Hello, everybody. Good to see all of you. I would like to introduce Paul Funk, whom I know all of you know. He's been with us since 2015 and is very active in a wide range of Los Serenos duties, which I also know you know. But did you know that Paul is also a certified interpretive guide, a certified naturalist, a certified fellow in production and inventory control? Presently, in addition to his work with Los Serenos, he also works with the Land Conservancy in their third grade program. Paul brings with him his experience from over 35 years in some form of manufacturing management. Phew, his energy abounds. Last but not least, I want to remind you that Paul developed this presentation with the help of one of our junior docents, Cole Bacon. Does anybody remember him? Cole has now graduated and is at UC Davis, and we believe he's a junior. It's all yours, Paul.
Thank you. Thank you. Everyone hear me okay? Okay,
yes,
good.
Paul.
All right, so today we're going to talk about Fresnel lenses, and I'm going to give you a history of them going all the way back to the very first lighthouse. And then from there, we're going to talk about the Point Vicente history and show you a little bit about how our lens is oriented, okay? So let's get into it right away. The very first lighthouse was the Lighthouse of Alexandria. What a landmark that was. It was at the mouth of the Nile River, right outside of the city of Alexandria, and on a small island called Pharos Island. It was about 40 stories tall. It's built out of limestone blocks that apparently they had cut in the mountains and floated down the Nile to build this thing. It's one of the seven wonders of the ancient world. They had a gigantic fire in the top of the tower there, and that was the light. Since it was so high, it was probably well over 300 feet tall. You could see it way over the horizon, and they said it could be seen for 100 miles. I highly doubt that, but probably you could see the glow of it for 100 miles since it was so high. They had a big bronze parabolic mirror in there to reflect the light out. And of course, it was a fixed light without any flashes. And I don't know where they got their wood fuel, but somehow they floated it down the Nile and then lifted it up to the tower with a dumbwaiter type operation. And that was how they ran it. It was pretty amazing. Obviously, they only burned it at night. They didn't burn it during the daytime, but it was very interesting. There was an earthquake in 1303 that really damaged the structure, and then it finally collapsed about 72 years later. And they decided, rather than just dump it, that they used the stones and they built a fort or a citadel on Pharos Island to protect the harbor with it. So that was the story of the first lighthouse. See, the problem with lighthouses in those early days is that the light was always produced by flame. And flame is not quite bright enough to penetrate the darkness on a real dark night, particularly if there's fog or any kind of clouds or something like that, right? So that's a big problem. In the early lighthouse illumination had flames, and the problem with that is that when you have a flame, it spreads in 360 degrees of light, right? So it's not focused in any one direction. It's diffused all around. So only 3% of the light source is directed towards the observer out there in the ocean, which is the mariner who is trying to avoid the rocks or the sand shoals or whatever it is that is the hazard. So they decided to build things where they could concentrate the light just a little more and get a little brighter light. So they had braziers where they actually had open wood or coal fires in there, and that was supposed to provide enough light, but really didn't. You could see it for about 100 yards. that's not quite good enough when the reef is a mile offshore. So not a good thing. Up in the Scandinavian countries, they use what are called vipifiers, and they use coal or wood, and they put it in a basket. You can imagine how bright that was. Not a very good situation. Later, they developed candles, and so they made candles out of tallow or beeswax, and the more candles, the better, they thought. All right, but it's still flames, and flames don't provide enough light. Later, they developed oil burning lamps. That was an improvement because it actually concentrated the light in the fire into a wick, which could be kept full of fuel, and that would give them a little bit brighter light, just a little bit. So they decided if you have one wick, that's good, but if you have multiple wicks, that's even better. And so a fellow developed this oil pan lamp with 10 wicks, and of course they're burning whale oil mostly. Sometimes they burn vegetable oil, such as olive oil, and that was the idea, but it still wasn't very bright. So later they developed a fellow named Argand, who was a contemporary of developed this capillary oil lamp. Now the idea is to take the wick and keep it constantly wet with fuel all the time. And as long as it's wet with fuel, then it'll burn brightly. As soon as it goes dry, then it will not only burn up the wick, but the wick will go out. And so they had to keep that way. So that this capillary oil lamp pulled the fuel right up to the wick, and it made a little bit brighter flame, just a little bit, maybe 2 or 3%. So then they recognized that they needed parabolic reflectors, and so they built this parabolic reflector system by a man named Stevenson. And this was okay. It improved the distance just a little bit, but not very much. And I'll show you a little later the problem with parabolic reflectors. Later on, they developed different kinds of wicks. This one was a concentric wick oil lamp. Instead of one wick, they had like 5 wicks, and they were concentric with each other. And so that would cause oxygen to be in between the wicks themselves, which would make for a brighter flame. So that improved the brightness by about 5%. Still not enough for the mariners that were out there trying to avoid the rocks. Okay, later they developed an oil lamp with a glass chimney. That helped a little bit. And then a fellow named Joseph Funk, no relation, who was the head of the machine shop for the Lighthouse board in New York, developed this oil lamp. And the oil lamp was used with whale oil in the beginning. And then he developed a flame spreader, which helped a little bit, and a glass chimney. Again, improving by 1 or 2% the brightness, but it's still flame-based, which isn't very bright. There was a pneumatic lamp that was developed to push the fuel up to the wick. There was a hydrostatic lamp developed to do the same thing. There was a hydraulic oil lamp to do the same thing. The idea, again, is to keep that wick wet with fuel all the time. So eventually, an improved oil lamp was developed by Joseph Funk. And he developed something that was a lot brighter than the previous ones, but still only about a 3 or 4% improvement. Along comes a fellow named Joseph Wiggum, and he found that he could get coal gas, and he could put that into a burner of some kind, and he had 108 gas jets in there. And they would turn this coal gas thing on, and blast a big blast of heat coming out of there, which was very bright and really nice. The problem was it was so hot that it melted the inside of the lenses. So that was not proved to be not very practical in about 3 or 4 years. Eventually, they found petroleum in the ground, and they were able to refine it into kerosene, and that changed everything. No longer did they need whale oil. After the 1870s era, the whale oil industry died out because kerosene took it over. And so Doty developed a wonderful kerosene lamp that had pretty good brightness and was adjustable. But again, it had a wick in it, and that wick had to be kept full of kerosene all the time. David Heap, a engineer with the Lighthouse board, developed an air pressure lamp that worked very well and did increase the brightness a little bit. And then Joseph Funk developed some more kerosene lamps a little later on. And then they discovered acetylene gas, which was a naturally occurring gas. And they were able to take that and turn it on and turn it off. If you've ever seen a welding torch, a welding torch uses a combination of acetylene and oxygen, and it produces a very, very hot and bright flame. Well, the idea was with acetylene, pure acetylene, they would turn it on and turn it off. And so they had a flasher that would let out a little bit of acetylene gas, and then they would ignite it, and it would really be a very bright flame. And that was quite an improvement, probably about a 10% improvement in brightness, but it was very short-lived flame. And besides that, the acetylene had to be put into tanks, and those tanks had to be hauled up the stairs of the lighthouse tower and put up there where the light was, and that got to be very tiring for the lighthouse keepers for a while. And obviously they only ran these things at night. So in the daytime, they developed a thing called a sun valve. And the idea was when the sun came up in the morning, it actually closed the flasher valve for the acetylene lamp and caused it to not work during the daytime. Then when the sun went down, it opened up the valve again and the lighthouse could start again. This was so revolutionary during that time that in 1907, it won the Nobel Prize for chemistry.
Wow.
For this thing, the sun valve. Yes, question? Okay, okay. And then later, they developed incandescent oil vapor lamps similar to a Coleman lantern. And they used oil, and they would atomize it and then ignite it, and it worked pretty good. Then later they got into electricity. But the problem with electricity was that it wasn't invented really until about 1857, and no light bulbs. They tried electric arc lamps. They tried other things like that, but all of these things required a gigantic steam engine or an internal combustion engine driving these very primitive magnetoelectric generators. And so George Siemens in Germany was the first guy to develop a reliable generator, but it required a big old engine to run it. And so lighthouses were very slow to adopt this because a whole lot of them were on islands or on structures that were offshore. Very, very difficult to get a great big piece of machinery over there and set it up to run that operation. So they looked like this, if you can imagine that.
Wow.
How would you like to see this building with a great big huge steam generator in there, steam engine running a belt which runs the dynamo generator. So these things were absolutely huge. The age of miniaturization had not reached them yet. They didn't have the technology to do that. So now here's what it looked like in Point Vicente. The building that is now the small museum there is this building right here. And this great big bull wheel machine right here is a gas-powered air compressor to run the foghorn. And I remember I moved up here in 1956. I used to hear that foghorn at night blow from the other side of the peninsula, and I lived on the east side near Mira Leste. Okay, that was a very, very loud foghorn at that time. Foghorn is gone now. It's been taken out. All of this equipment has been taken out and scrapped a long time ago. But that was the thing that was necessary at that time. And the belt-driven machine you see there is the generator that actually provided the power to turn the light and also light the light. Okay, so this was Point Vicente in the early years. All right. What else do they use for illumination? Well, they use electric arc lamps. And the idea was to have an anode and cathode, right? Two carbon elements coming together, and they run electric current through that, and a huge spark would come out of that. And that's great. The problem was that it melted the carbon points, and they had to be readjusted to have this distance between them so that the spark would be there. To make sure that that happened well, they designed all kinds of different types of carbon points, and some had graphite inside of them and other things, just so they would last longer. But then along comes Thomas Edison, and after 10,000 tries, he finally developed a tungsten filament light bulb, and that worked very well for lighthouses. Eventually, he developed a 1,000 watt light bulb for lighthouses, great big one. And that was in use for a long, long time. They even got up to about 1,500 watts, which is a very, very powerful light indeed. But then later in about 1952, towards the end of the 40s and early 50s, they developed halogen lights. And that was a much more compact and far more reliable light than the incandescent light bulbs, and have about an 18-month life. And so that's what they use now. So Point Vicenti's inside the Fresnel lens in the tower was this 2-bulb automatic lamp changer. And the idea is if one bulb burned out, the other one came on automatically. The lighthouse keeper would have to come in and wipe the dust off of these things every day, just to make sure that the optical clarity was there. All right, and the big problem that they had in Point Vicente was when they first opened in 1926, they had this generator that I showed you, but it only had enough power to turn the light and to light the light. And so all these outbuildings had to be lit by kerosene lamps. It took them until 1935 until Edison finally brought power all the way out to Point Vicente.
Wow.
Pretty amazing. All right, so the problem is, how do you take this low power flame light and make it bright enough to see from ships at sea and project it far enough away from a hazard that it keeps ship from crashing into the rocks or the sandbars or whatever? Well, let's talk about a few properties of light here. When we did the presentation in 2018, Cole and I actually had visual aids where we would show experiments using these things, but I'm just going to show you the 40,000 foot view, just the concept. The concept of reflection is a change in direction of light at a particular surface, like a mirror or something like that, okay? And then there's refraction. That's a bend in a beam of light caused by light changing speed. So if you look at a pond and the pond has fish in it, you would see the fish down there. And if you reached your hand where you think those fish are, you would not touch the fish. The reason is the light is being bent. The reflection of the light off the fish is being bent, and they're actually at a different place than where your hand goes, right? So that's refraction. Then there's collimated light. This is a very important concept for lighthouses because it's the principle upon which the Fresnel lens was built. The idea is to point all of the light beams that you can in one direction. I showed you before a naked light that was lit, naked flame that was lit, and the light would be going in 360 degrees, right, all over the place. In other words, it's not capturing all of the light and pointing it in the direction of the ship. In fact, it's all over the tower, etc. So the idea is to capture that light and put it in one direction. Okay, there's diffraction. That's a spreading out of light waves from an opening or a slit. And then there's interference. That's when different light waves combine together. Sometimes it actually causes a blackout. Other times it causes a huge magnification of the light, depending on the light waves. And then there's polarization. That's like polarized sunglasses, where you can look into the water and see deeper into the water and see details under the water. That's because it's oscillating the light waves only in one direction. All right, so a Dutch physicist named Huygens was the first one who developed the theory of light waves. And NASA immortalized this guy by actually naming one of their probes after him that went onto one of Jupiter's moons recently, right? The Huygens probe. So Huygens developed this mathematical theory of light, and he talked about it as wave fronts. And along comes Isaac Newton. He says, no, that's not right. No. Light is corpuscles. These are little round and tiny and little particles of various things. And so that was his theory. But he was unable to explain diffraction or polarization or interference. And so eventually they dismissed Isaac Newton's theory, even though he was the preeminent scientist of the day. He's the one who discovered gravity and other things, right? So along comes a fellow named Fresnel. Augustin Jean Fresnel was actually a civil engineer trained as a road builder. He hated that job because he had to ride his horse all over the place and supervise road building all over. And it was just very boring work. And so as a hobby, he got into studying optics, and he became a really, really brilliant and far-reaching optical engineer. Then he refined Huygens' theory of light waves. As an engineer, he did it mathematically. I've looked at his equations. They're absolutely phenomenal and very, very detailed. And so he developed that and discovered polarization and diffraction. And he invented a lens that would collimate light for very long distances. That was his claim to fame. So as a result, he was hired by the French government in 1819 to extend the range of lighthouse beams. The problem with Fresnel was he was very sickly, suffered from tuberculosis, and he died at age 39. So the actual body of his work was done over only 10 years, which is really amazing, considering the amount of work that he was able to produce. So he had this theory that light travels in transverse waves due to electric and magnetic forces. And so he won the grand prize of a competition that provided an explanation for diffraction of light. And that was competed with Isaac Newton, and he won. So he became a celebrity, and they hired him to increase the distance that light could be seen from a lighthouse. So let's talk a little bit about candle power. Candle power is used to compare the intensity of light and distance between different lighthouses. So one could have 2 million candle power and one could have 500,000 candle power. But the candle power is not a very good, I don't want to get into these details here. It's not a very good measurement of the power of the distance that light can travel, because there's other factors. One of them is elevation above sea level. So on a clear day, if you're down at sea level, you can only see 36 miles before the curvature of the Earth blocks what's past that. So here we are. If we're at the base of our cliff, underneath our point and center interpretive center, we can see the very tippy top of the hill on Santa Barbara Island, which is 36 miles out. That's because it's high enough to be just above the curvature of the Earth. On the other hand, when our light is 185 feet above sea level, you can see the entire island because it's high enough so that it could be mounted on a bluff. The cleanliness of the lens and the light bulb is really important. And so those guys would be out there washing the inside and outside of the windows of the tower and cleaning the lens and the light bulb. And the cleanliness of the windows is really important, and also the transmissivity of the atmosphere is important. So when we have real smoggy days, you can't see very far. And the rotation speed of the optic or the lens is really important too. And the ones that go slower can be seen further. Okay, so all of those are things that have to do with candle power. Now, there was parabolic reflector systems that were developed, and the idea of that was to increase the distance that the light could be seen. Now, again, they're using flame-based lights here, right? So they would take a parabolic reflector and put it behind the light source, and that would help. Instead of 3% of the light being seen out offshore, it would be up to 39% of the light develop. But the big problem with reflectors is 50% of the original light is lost when that light changes direction. So that's a serious problem. So what they did was they put tons of reflectors out there, and the idea is if one reflector is good, why not 14 of them? And that was good, but and it helped a little bit, but even then, the sea captain said, we can barely see that light. Come on, it's just a flame against a little reflector, and it's just not bright enough. So Fresnel took a look at this and said, you know, we need to collimate the light. And the best way to do that is with a convex lens. But the problem was to have one in a lighthouse, it'd have to be so huge, and it'd have to weigh so much that we probably wouldn't be able to get it up to the top of the tower, first of all. Second of all, in 1819, the glass making technology was lousy, and they were producing what we might call Mexican glass today, which means it has a lot of bubbles in it, a lot of waves in it, optically terrible. And so they had a big problem trying to produce a decent convex lens. And so that isn't going to work. So he decided that if he took the parts of the convex lens that are not needed away, in other words, actually machining it so that only the parts that are necessary would be there, then he could produce the same effect as a convex lens, but a lot lighter and probably a lot more effective. So that's what he did. And as a result of that, he was able to collimate light, actually point it in one direction. Now you notice these prisms here. You see how the light goes in the very center? The light goes straight out. That's called a bullseye lens. And then the other lenses actually bend and refract the light and reflect the light. So we'll see how that goes. So dioptric lenses are those that are based on refraction of light, that's bending of light, focusing light through the lens and not reflecting it off a mirror. And then catadioptric are the ones that both reflect and refract the light to capture it that it would otherwise be lost. So and that's the upper parts of the lens. And in the very center of the lens is the bullseye. That's the actual flasher. That's the central convex portion that helps orient it and intensify the beam at the center. So it looks kind of like this. This happens to be a barrel-shaped lens. Ours is a clamshell-shaped lens, but it's the same idea. In the center is the bullseye, and then to the both sides are dioptric lenses, and then there's catadioptric. So when the light hits that bullseye, it actually goes to the other prisms as well and points all of those light beams directly to the place that they want it to go, which is offshore. So Fresnel lens can be either barrel-shaped or clamshell-shaped, and they magnify and concentrate visible light, and it gets collected and intensified and redirected it directly out to sea, and the light input is increased dramatically. So look at this. This is the original prototype lens, the one on the left that Fresnel developed. He had to mathematically determine the measurements on all of these pieces and trapezoids and put them together and come up with this lens. It was just amazing piece of engineering just to come up with that. Now remember that the glass technology in those days was lousy, and so he did the very best he could with the technology that he had, and still it was much brighter than the previous ones. A little later, he got with the glass manufacturers, which were government-owned facilities, by the way, and he got them to produce circular pieces. And then he developed a much more effective lens from that. All right, so the idea of collimating the light comes from that bullseye portion of the lens, the very center of the lens. As a result of that, over 80% of the light was directed towards the observer, which is a big, huge improvement over the 3% of a naked flame, or a 39% of a parabolic reflector frame. Huge. And so as a result of that, the mariners who would sail by the French coast could now see the light, and they could avoid the obstacles that were there. And it was very important discovery to do that. So Fresnel lenses are in various sizes. They're called orders. The very biggest one is the one in the lower left corner. It's called the hyper radial lens. That's the largest in any lighthouse in the USA. There were 3 of them made over time. One is in Pakistan, another was destroyed, and the other one is in Makapu Point in Oahu. That is a huge lens. It's about 25 feet tall. It's about 10 feet in diameter altogether. It's a fixed light. It does not flash, but it's up on a big point there that's 1,200 feet above the ocean. And so as a result, it can be seen for about 40 miles out. There is a first order lens. It was at Point Conception, right here above Santa Barbara. After it was decommissioned, it was moved to the Santa Barbara Maritime Museum. You can go there and see that thing. That thing is absolutely beautiful. It's 20 feet high and about 8 feet in diameter. And they have a marvelous display there of the whole thing. It's really amazing to see. I highly recommend that you go to the Santa Barbara Maritime Museum. We have a third order lens. That's a point vicinity lens. The 6th order lens was usually used very small. It's only about maybe 24 inches high. And that was, for example, the San Pedro Angels Gate light. And if you go to the San Pedro Maritime Museum, you can see that as Angels Gate light, the 6th order lens there. So all of them have different focal points, and the idea of the focal point is how far it will actually travel through the atmosphere, right? So ours had a focal point of about almost 20 inches. There's 3 basic kinds of lighthouse lenses, right? There's a fixed beam lens, there was a rotating lens, and there was a rotating and flashing lens. Ours is a rotating and flashing. The 4th one down there is called group flashing, and that exactly is what we were. And I'll show you in a little while. These are called characteristics. Every lighthouse had a unique flashing characteristic or non-flashing characteristic. And the idea was those characteristics were noted on nautical charts so that a sea captain going by could see if there were 3 lighthouses in the area. He could see that each one had a unique signature. He could plot his course or plot his avoidance of any hazards based on which lighthouse that he was looking at. And so ours was that, and they were, those characteristics, flashing characteristics, were developed by a combination of lenses. And the original one was developed by Fresnel. The first flashing first order lens was developed by him, and it turned out to be 3¼ times as powerful as the best reflectors then in use, which was huge for them. What a big difference. Now today, obviously, we have even more effective reflectors and not reflectors, but projectors of the light. 8 more trapezoidal lens panels on top, and so the duration of the flash was double that of the lens of the flash alone. Very important. You could have multiple characteristics using colors and other things. For example, the characteristic of the San Pedro light was green, and the reason for that is because ships would be coming down the sea lanes from the north to the south to get into the harbor entrance at San Pedro. In a ship, the left running light is green, the right running light, or the starboard running light, is red, right? So the light was green to show that you had to make a left turn into the harbor. And that's why the San Pedro light was green. So that's another way of looking at it. There was a fixed characteristic, like this one on the right here. There could be a flashing characteristic, such as ours, where you have multiple bullseye lights, or a group flashing, like ours. And this is more like the Point Vicente light right here, where you had 2 bullseye lenses right together, and it would cause flash, flash, just like that as they went through. And then the one on the right is the Bishop's Rock Lighthouse, right offshore of Great Britain. They actually had 2 lenses stacked on top of each other for a long time, and that was a unique signature as well. Okay, so this could be, you could have something called occulting, which means that they would drop a can or a cylindrical metal sleeve over the light from time to time, and then lift it up, and that would cause a different type of flash. So here's our Point Vicente lighthouse. It had a 0.3 second double white flash, then 4.7 seconds of dark, and then 0.3 seconds, another double white flash, and 14.7 seconds of dark or eclipse. So if you add that up, that's 20 seconds, right? So every minute there were 3 revolutions, and it would be those flashes every minute. So the manufacturer of our lens was Barbier, Bernard, and Turenne, a French company, and had been around since 1867. They reorganized in 1901 and brought this fellow Paul Turenne on as a partner. And so the initial BB&T was first used in 1901, and ours was built by them. Now, there's at least 3 local histories, including Maureen McGovern and others, who claim that our lens was manufactured in 1886, and it served in a lighthouse in Alaska for over 40 years before being transferred up to our organization, up to Point Vicente. But it can't be right, because the lens was manufactured by BB&T, and they're not called by that name until 1901. So there couldn't have been 40 years earlier. There were no lighthouses in Alaska until 1902, and that would be 24 years prior to when they actually opened Point Vicente. So no way could it have been in Alaska. So the lighthouse was built from 24 to 26, and therefore the lens would have to have been built between 1902 and 1924. But during that time was World War I between 1914 and 18. And they had to take all of the lenses and put them down in the catacombs underneath Paris to hide them from the Germans so they wouldn't be taken. And they did that. And then after the war, then they brought them back up, and apparently they shipped it to Point Vicente at some time after World War I. All right, so there were all kinds of detection systems that were used for lenses. And they had drive gears that were either on a ring, either on the inside or on the outside of the pedestal itself. Now you notice these wheels here. These are called Chariot wheels, and the idea is the lens platform rests on those Chariot wheels, and they're made of brass, which is not a real strong metal. And after a while, because of friction, it wears down, and they actually have to lift up the entire lens and replace those wheels from time to time. That system was developed by Fresnel, Now, later, in about 1903, they invented electric motors. And so since our lighthouse was installed in 1924, they were able to use an electric motor to turn it, which was far more efficient than the clockwork systems that were being used in those days. And those are similar to grandfather weights that were pulling on a series of gears to actually turn the lighthouse, the light itself. And so that's the way that goes. Another problem then, how do you support this weight and keep it rotating? Well, the problem that we had was friction. So because there's a lot of friction in these real heavy lenses, some of them, our lens weighs around 2,800 pounds. Okay, the big first order lenses weighed 6,000 to 7,000 pounds, a lot. So how are you going to turn that so that because of friction, so that you can get the proper flash? Well, the idea is that they would add more bullseye flash panels in there, and that would cause flashes to occur more often, but it's very expensive to produce those things. And the idea was it wasn't very effective. So they designed 3 different ways to support these lenses. One was with wheels, I just showed you. One was with ball bearings, and another one was called Mercury float systems. I'm going to briefly run through those and show you what they are. This is the Chariot wheel system that was developed by Fresnel in 1822, and they rotated with very little friction, or as little as possible. It worked real good for smaller lenses, but as soon as you got great big ones, the wheels would wear out in about a month or 2. So they had to replace them constantly. Then a fellow named David Heap, who was a wonderful engineer for the Lighthouse Board in New York, developed this system, which was a series of ball bearings. And this is exactly what we have at Point Vicente. The ball bearings that we have in supporting our lens are as big as baseballs. There are 16 of them, and they were very, very easy to replace. Just lift up the lens and replace the whole ball bearing mechanism, or replace each bearing. Similar. So that worked very good. And finally, they had Mercury float systems. Mercury is a liquid that has a very, very high density. So you would need a lot less mercury than water to float something on it. And so Fresnel himself proposed the use of this system, but it wasn't until 1890 one of his lieutenants developed this thing and made a workable float. This is really an incredible thing. You have a bath here, and the bath would have mercury in it. Then they would put the lens support ring on top of that and float it on top of the mercury. Jim, the fellow who came and installed our lens, told me about this. He said up in Piedras Blancas, they had a system like this, and you could actually take that lens and with one finger move it to the left, and the entire lens would rotate because there's no friction whatsoever. So this was really good. The problem was mercury was very toxic, and it had to be replaced once a year. And when they did that, the lighthouse keepers would get mercury poisoning. Some of them would die. It's not a very good thing. Here's some mercury float pedestals that were made. Very interesting setup. All right, the human history of the Point Vicente Lighthouse is like this. Until 1939, the U.S. Lighthouse Service was a unit of the Treasury Department. Go figure. No idea. The reason that they didn't adopt Fresnel lenses faster was they had a couple of misers and skinflints that didn't want to spend the money to buy French lighthouses, lights, and so they used American-made ones, which were very ineffective. And eventually, the sea captains got all over their case and showed them that how great the French lighthouses were, and they tried a sample of one at Sandy Hook Lighthouse, which is at the entrance to New York Harbor. It worked so well that they eventually they fired the guy that didn't want to buy the French lighthouses, and they bought a whole bunch of Fresnel lenses and started installing them in lighthouses up and down the East Coast and then up and down the West Coast after that. So all Southern California lighthouses, all California lighthouses were automated in the 1970s. And then the administration was moved from the active Coast Guard to the Coast Guard Auxiliary. Our lighthouse was opened in 1926, took them 2 years to build it. And the first lighthouse keeper was a fellow named George Leomado. And he had 2 assistants, Harry Davis and Ben South. And the big problem with that was Leomado was a drunk. And when he got drinking too much, he got nasty. And he started calling his assistants names and threatening them and other things. Eventually, they brought him up on charges to the Lighthouse Board. All 3 of them were reprimanded. Leomado was transferred up to Piedras Blancas. He got along well with those people up there, apparently, but Harry Davis and Ben South stayed on here in Point Vicente. The guy who actually had the most to do with what Point Vicente looks like today is Anton Trittinger, an interesting guy. He came from Switzerland, where there are not a lot of lighthouses, last I heard. How he ever got into the lighthouse business, I have no idea. But he came and with his family, and they, at that time, Point Vicente was really out in the sticks. There was no houses nearby or anything. There was a few Japanese farms and things, but nothing else out there. So this picture that I have is the only one I could find. I did a lot of research trying to find a picture of him and his family. He had 2 daughters, and they used to go to school at Malaga Cove School, and they used to ride the farm tractors to school every morning. Very interesting thing. Anyway, this is his passport picture. That's the only picture I can find of him. And it's a picture of him displaying the Lighthouse Efficiency Award, which he won for several years. And he was the keeper for 15 years, from 1930 to 1945. He's the guy who planted all of the landscaping. He planted the palm trees and all of the other trees there, and actually built the place up to be really like a park. Very beautiful. He had several good assistants at that time. And here is Tom Atkinson, one of his assistants, polishing the light bulb. And then later there was Ed Schott. He's replacing a 1500 watt light bulb that they had. This is before they got the other light bulbs that they use later. Okay, so the idea it has to be polished every day. The last keeper was Joe May, who was the assistant to Anton Trittinger for 5 years before he became the head keeper of the last head keeper. There was a wonderful article in the LA Times about him retiring in 1955, and he had lots of reminiscences about the lighthouse and about the things that occurred during that time. Very interesting guy. After that, a series of Coast Guard people ran the lighthouse until 1970, when it was finally automated. Now, what's going to happen to the lighthouse? Well, we have the lens, we have the Fresnel lens, but the lens that's replaced it is this programmable LED lighthouse beacon. And it has exactly the same flashing characteristic, a double flash every 20 seconds. And it's all electronic, there's no moving parts. But the thing is, it only has a range of about 14 miles instead of 20 miles. When the Fresnel lens was actually operating, I went to Catalina several times. I could see it flashing from Catalina, and that's 21 miles from Point Vicente at where I was, over there at Two Harbors. So it had a tremendous range, but this one only has a range of about 14 miles. Really, it's not necessary that it has such a long range anymore, because the lighthouse itself is not used as an aid to navigation, except for historical purposes now. They have GPS and they have other techniques now that the ships use, and they have a ship channel where they have to be offshore 3 miles minimum. And that keeps them completely away from any reefs or any problems, except for the Dominator, who came in on a foggy night and with a drunk captain and slammed into Lanada Bay. And that's the way that goes. Okay, so these lights are made by a company called Vega. It's a very interesting company. They are worldwide, and they have the finest technology that there is in this area. And they have these things that can be controlled remotely. And in fact, they are controlled and adjusted remotely from the terminal island base of the Coast Guard, which has a responsibility for all of the lighthouses from Point Conception to the Mexican border. All right, so this is the last picture of the lens itself in the tower as it was up there. And boy, I can remember going up those stairs and actually looking at the lens right in the tower, which was really amazing. Now, they had to keep this thing clean all the time, and so that the lighthouse keepers would be in there minimum of once a week, cleaning it on the inside of the windows and the outside of the windows the same way. And now it's in our facility right now. This is really a wonderful display that was developed, and praise God for Jim, the wonderful lampist that was able to take it apart piece by piece and then put it all back together again and refurbish the whole thing. It's absolutely beautiful. I hope you get a chance to actually look at the video that was made about them disassembling and reassembling the light. It's a very, very interesting thing to see. So that's all I had, and I hope that you really enjoyed it.
If anyone has any questions for Paul, please unmute your mic and ask them now.
I have a quick question. This is Diane. Can you hear me?
Hi, Diane.
Hi, everybody. Happy New Year. Paul, that is fantastic. I know a lot of it probably went over, I have to speak for myself, over my head with all that chemistry and measurements, but it is a beautiful lens. If I can remember, since we haven't been there for a while, it has different colors. And my question was about the colors. And you had mentioned, like in the San Pedro Harbor, you know, one color has you turn left as you're entering. Is that the same with the lens when it was in the tower, where those different colors represented something?
Yeah, actually, our lens is a monochromatic lens, which means that it's basically clear. There are no, it's slightly greenish. If you look at the prisms, they're slightly greenish.
Right.
And that helps in the refraction of light in the dioptric and catadioptric part, in the outside portions of the lens. But the San Pedro light was green on purpose, as I mentioned, because it's the same as the port light on a ship.
Thank you, Paul.
Okay.
Thank you so much.
Paul, we do have a question from Jan. How big is the new lens?
How big is the new lens?
Yes.
You mean the one that's in the tower now?
Jan, do you want to clarify your question, please?
Yes, the new one. How big is it?
Yeah, okay. It's about a total of 4 feet tall. It's not that big, but it has very high intensity LEDs in it. And those things can be projected 14 miles from that. And again, no moving parts. So it's very easy to maintain and to adjust and to work. It's quite a piece of engineering. What's interesting is to see these Fresnel lenses that have alternating color panels. So the one I showed you that has red and white, for example, is on Lake Superior in Michigan. And actually, they rotate red and white and red and white like that. And there's many other colors that have been developed as well. These are fantastic pieces of engineering, folks. The amount of mathematics that went into the original design is stunning, really stunning. If you can get a chance to see that, and it's a concept that revolutionized the lighthouse and the safety of ships at sea. Other questions?
Okay, if there are no further questions, this concludes today's presentation. Just be aware, everyone, you can hang on and chat with people a little bit after the presentation if you want to.
Thank you, Paul.
Thank you, Paul. That was
Thank you,
really
guys.
great.
Thanks, great, Paul.
Thank you,
Thanks,
guys.
Paul. Very informative as always. Great.
Paul,
Thank you.
last minute question.
Go ahead.
I was under the impression that this was a Mercury bath, a rotating system, and you've corrected me that it's a ball bearing system. Is that
That's
correct?
right. That's correct. Yeah, if you look at the video of them reinstalling the lens, you can actually see the ball bearing base that's underneath it, and the balls themselves are the size of baseballs. There's 16 of them.
Well, thank you. I had that wrong.
Hi, Paul. This is Christine.
Hi, Christine.
Can you, maybe you have said it, but I probably missed it. There's a zero order lens in one of the view graphs you have. And what is the difference between, what is that compared to the first order to sixth order?
The older
you-
lens, you say?
Yeah, you have that thing written down as hyper
Radial.
yeah.
Okay. The very biggest lens that was ever made, and they only made 3 of them, were hyper radial lenses, and they are bigger than first order lenses.
Okay.
Okay, so
But they're not, they don't make that anymore because,
no, they have not made them for years and years and years because they're so difficult to make. You know, we're talking thousands of prisms, and the things are the hyper radial lenses are 25 feet high by about 10 feet in diameter. What's interesting about that is the one on Makapu Point was actually used as a target by some local idiot kid with a high-powered rifle. And he actually shot out several of the very valuable prisms that were made in the late 1800s. Unbelievable.
Wow.
So Jim, our tremendous restorer, worked with a company in Florida that has the ability to take these lens pieces and model them in a computer-aided design program, and then cast them in acrylic plastic, which is ideally suited to match the exact color and the exact refractive and reflective capabilities of the original glass. And so Jim went in there and took out all of the destroyed prisms and reinstalled them in that incredible hyper radial lens. He said it took him about 4 months to replace all of the broken out pieces that had been destroyed. But they have restored it to full order, exactly like it was brand new now.
Wow.
I don't know if any of you met Jim when he was here in 2019 February, installing the system. What a tremendous guy. He lives in Tucson, Arizona. He served 40 years in the Coast Guard. and has gone to all of the Coast Guard schools regarding Fresnel lenses, et cetera, and probably teaches a whole lot of those things. He's one of 4 certified lampists in the United States that's allowed to work on these lenses.
Wow.
And he worked with a team of guys from the Terminal Island Coast Guard base. And those guys all came at the opening that we had at Woad in 2019. And it was phenomenal to see all of them together in one place.